often in real problems, it turns out that two different variables are changing with one another in the problem. As an example, suppose I'm standing in a position and I'm watching a train go by. And you think about the angle, my eye angle, sort of looking at the train. As the train goes by, you know, when it's far in the distance, I'm just kind of looking like this. And then as it gets closer, I start to move a little bit, and then it goes by like this. That is, I'm changing the rate of turn of my head to see the train. If the train is a long distance away, you don't really notice very much of a change. But if the tracks are right here, then I'm looking at the train, and here it comes, and then all of a sudden, whoom, it goes by. And so I'm moving very quickly. Now, we have a wonderful ability here in calculus to freeze time. This derivative idea is a change at a moment, rate of change at a point, rate of change at a point in time. So we're going to sort of freeze time with a couple of problems here in just a minute. But I just want to tell you that now the variables that are changing, the angle of my head is one variable that's changing in this problem. But maybe the speed of the train has a lot to do with it too. It does have a lot to do with it. The speed of the train is a factor. The distance that the track is from me, those are all factors in the problem. And if we can somehow relate those ideas with equations, and use the idea of derivative, then we can find out all sorts of stuff. Take this problem as an example. A rock is dropped into a pond, causing circular ripples. If the radius of a ripple is increasing at 1 foot per second. Now let's stop right there and let's talk about that. So a rock is dropped into a pond, a splash is made, and here goes a ripple. And it's a circular ripple that's coming out. And it's going out from the center at a certain rate. All right, that's what we're talking about here. And that rate can be measured by the change in the radius. So that the radius of the circle is moving out. Now let's continue. So the radius of a ripple is increasing at 1 foot per second. At what rate is the area of the circle increasing when the radius reaches 4 feet? So as that circle, you see, is growing larger and larger, the radius is getting wider and wider, the area is getting bigger and bigger, the area of the circle is getting bigger and bigger. Now, can we freeze time when that radius gets to be exactly 4 feet? Sure we can. And the freezing of time and thinking of a rate at a moment in time is what derivative is all about. Now just understand too that this transition or this calculation of derivative, the notation of it, what does the notation mean? Well, come over here and let's take a few examples so we can get a handle on this. That if a train is going 30 miles per hour and x is some distance traveled, then the derivative of x, dx over dt, the derivative of distance in terms of time, is a rate. It is the 30 miles per hour that we're talking about up here. Change in distance per unit of time. Change in distance, change in time. If a fire hose is kicking out 25 cubic feet of water per minute, 25 cubic feet per minute, you see that's sounds like kind of a rate. But if we're talking about the volume of water that is involved here, and firemen might want to know about the volume of water that they're putting onto a roof, and how much it weighs and all sorts of stuff like that, so they'll know when the roof is going to collapse. But at any rate, the notion is if the fire hose is putting out 25 cubic feet per minute, then dV over dt, the derivative of volume according to time, we're freezing. We're talking about the rate of the volume at a moment in time is 25 cubic feet per minute. You see this direct correspondence here, and here is our interpretation in calculus for that idea. Now this one is a little more elusive. We have to reach out for this one a little bit. A car has a certain RPM, the engine is running at a certain number of revolutions per minute. The shaft is turning over at this rate, revolutions per minute. Now, if theta is the angle of revolution, you know, if it's just a change in angle. When we're going around and around, it's kind of like my head turning. That's the change in theta, you see, and some kind of angle when we're just moving around like this. So theta is an angle of revolution, then d theta over dt means the derivative of theta in terms of time, or it's a frozen moment. It's a rate of change in theta at a point in time. And that's just 2,500 RPMs. Now, if we're talking about this theta angle business, now angular change is according to a theta within a circle. And you know that a complete revolution of a circle is an angle of 2 pi radians. So if we put that idea, this RPM, revolutions, well, each revolution is 2 pi. So this would be 5,000 pi radians per minute, you see, is this angular velocity that we're talking about here. Well, okay, so our notion of derivative allows us to freeze a moment in time. And all we need to do in problems such as this one is have a relationship between the variables. And there's a nice built-in relationship between the variables here. We're talking about radius changing, area changing. We have a formula that relates area and radius. It is the area of a circle is pi times radius squared. Now notice what we're doing here is this circle is changing like this. This circle is going out, and at the moment in time when that radius reaches 4 feet, we want to know where, at what rate is the is the area of the circle changing. Okay, so area is pi r squared. Now, implicitly differentiate on both sides according to time. According to time. This rate that we're talking about is a rate, a volume at a moment in time. So we are differentiating with respect to t. And so here we have a dA dt, the change in area at a moment in time, or with respect to time. And on the right, we're doing the same thing. We are differentiating with respect to t. We're differentiating the radius with respect to t, or r with respect to t. So implicitly it is, let's see, 2r, pi times 2r, and the dr dt with respect to time. You see, radius with respect to time. Now, what do these things mean? Well, this is what we're looking for. If we're thinking about what is the change in area at that moment in time, that is what dA dt is. That's the symbol for it. And dr dt, well, we were talking about the rate at which the radius is changing. It's changing at a constant rate of 1 foot per second, we were told. So this dr dt is 1 foot per second. And we're talking about at the moment that we're making this calculation, the radius is 4 feet. So this is 2 times 4, or pi times 2 times 4, or 2 pi times 4. Now, I'm putting the units in here so that we'll be able to look at the unit in our answer. A lot of times, if it's at all confusing, all you have to do is put the units into the problem, and the unit at the end of the problem drops out very nicely. So here we have a radius of 4 feet. We have 1 foot per second, and then we have feet times foot, or feet times feet, feet squared, square feet. So square feet per second is the unit down here. So it's 8 pi feet per second is the rate of the change of the area of the circle at that moment in time when the radius gets to be 4 feet. Here's another example. A balloon is inflating at 4.5 cubic inches per minute. So a balloon is being blown up, and 4.5 cubic inches of air per minute is being put into the balloon, and the balloon is expanding. Find the rate of change of the radius of the balloon when the radius is 2 inches. So at the point where the balloon grows to a radius of 2 inches, at what rate we're saying, let's see, find the rate of change of the radius when that radius reaches 2 inches. All right. We need a relationship between volume, or how do we think about the volume changing in this kind of figure. It's a sphere, you see, or it's roughly a sphere. Actually, it's not exactly spherical, but it's close enough for us to make the calculation. All right, the volume of a sphere is 4/3 pi r cubed, and oh, by the way, this 4/3 pi r cubed, this volume formula comes from Archimedes, and if you ever get a chance, you should read about the derivation of this formula and what Archimedes did to derive this, to find this formula. Very interesting situation. Archimedes himself is a very interesting character historically. One of the 3 great mathematicians in all of history. Anyway, the derivative, the implicit derivative is, let's see, this would be a dv over dt. This would be 4/3 pi 3r squared. Now the derivative is the derivative of radius with respect to time, so it's a dr dt. Now what are we looking for and what do we know at this point in the problem? Well, when we're asked to find the rate of change of the radius, you see, at a point in time, that's the dr dt. So we're looking for the dr dt here. We're looking for that. Now, so we need to solve for that in our problem. Now, what is this then? What is dv dt? Well, that's the change in volume in terms of time. And that change in volume is nothing but this. We're just adding a constant 4.5 cubic inches per minute. So that's really what this part is. Well, let's clean up a little bit. We have, let's see, the 3's go out here, and we've got 4 pi r squared times dr dt. Now, I've repeated that up here. So 4 pi r squared dr dt on the right. And we're just plugging in for this volume rate at a moment in time. That's the 4.5. And then dividing on both sides, let's see, by this coefficient, this would be 2 squared. Oh, incidentally, I popped in the radius of 2 because it said we're calculating this at the moment that radius reaches 2. When that balloon is expanding and the radius reaches 2, what is the rate of change of the volume? That's what we're asking. Okay, so the 2 is popped in here for radius. 2 squared is 4. 4 times 4 is 16. This is 16 pi. Dividing on both sides by 16 pi, we get this. And we find that dr dt is approximately 9/100 inches per minute at that moment in time. An airplane is flying at an altitude of 6 miles on a path that will take it directly over a radar tracking station. If the distance from the radar station is decreasing at a rate of 400 miles per hour when the distance is 10 miles, what is the speed of the airplane? The confusing part here is the notion of the 400 miles per hour when the distance is 10 miles. You see, the airplane is not coming exactly straight toward the tracking station, but the distance between the radar unit and the airplane is decreasing at 400 miles per hour at a certain moment in time. And that moment in time is when the distance between them is 10 miles. Let's outline our information. We know that the altitude of the airplane is 6 miles. The distance between the radar unit and the airplane is decreasing at 400 miles per hour when that distance between them is 10 miles. And we're looking for the speed of the airplane. Here's a diagram. Here comes the airplane, and at this one moment in time, the airplane is 6 miles high, and it is approaching the radar unit at 400 miles per hour. So that distance is decreasing at 400 miles per hour at the moment when that distance is exactly 10 miles. This is the notion in terms of derivative of some derivative in terms of time, or some d dt. Now we haven't attached a label to that variable distance, so we don't have an additional letter in the numerator. But that's what we're going to come back to in just a little bit in our problem. What we're looking for here is the speed of the airplane. Well, we have a right triangle situation. Let's put some labels on this. Let's call the distance between the airplane and the radar unit S. And to complete the triangulation, we'll call this value x. Now, it's the change in x that we're really looking for here, because it's the change in x that's the speed of the airplane. And if we flip-flop the right triangulation, we can see it even better. So we're looking for that change in x. Now, the relationship, because we have a right triangle, is x squared plus 6 squared is s squared. And we can go through and differentiate implicitly through the problem. So for the first part, it would be, to differentiate x squared, it's 2x, and it's a dx dt. And for the constant just goes out, and for s squared, it's 2s, and it's a ds dt. Now, the change in x with respect to time is really what we're looking for here. That's the speed of the airplane. So we want to solve for the dx dt in our problem before we go any further. So with our equation, we'll divide on both sides by 2x, and we have some nice expected cancellations on both sides, so dx dt is equal to this. Now we have some information about the expression on the right side. S is exactly 10. That distance from the airplane to the radar unit you see was s, and that distance is 10 at a moment in time. The ds dt is the change in that distance with respect to time. And that was the 400 miles per hour. Now, we could list this here as 400 miles per hour. I could list it as negative 400 miles per hour because it's a decreasing distance, but it really doesn't make too much difference in this problem. Now, the x is an interesting matter. You know, x is this part at the top, and we can actually make a calculation for x at a moment in time when s is 10. So we can let s be 10 and solve for x. And we can do that by taking this relationship at the top and just make the replacement for s. When s is 10, then we would have 10 squared on the right. So we'll have 100 minus 36, so x squared is 64, and x then is 8. And we just pop that x of 8 into our equation, and we'll solve for the dx dt. dx dt is 500, and that's 500 miles per hour. So the speed of the airplane when s is 10 miles is 500 miles per hour. Here's a problem that involves an internal combustion engine. It says a 7-inch connecting rod is fastened to a crank of radius 3 inches. We'll look at a drawing of the connecting rod and the crank in just a moment. But let's continue. The crank shaft rotates at a rate of 200 RPM. Find the velocity of the piston when theta is pi over 3. Sounds like a complicated problem when you first look at something like this. And a diagram helps a great deal to begin to give clarity to what's going on. What we want to do is understand the nature of the problem, first of all, and then get into the mathematics of it. So we'll understand what's going on in the problem. Then we'll look for some kind of equation that relates the unknown values in the problem, or all of the values that we're talking about in this kind of problem. And then we're going to decide on this differentiation, the implicit differentiation, and what that does for us, and understand what that differentiation is requesting or what the parts of it mean. Let's go through the process. All right, we have our problem given here. The problem refers to this cross-section of an engine cylinder. This is the cylinder being referred to. Here's a piston within the cylinder. The piston is moving back and forth, and the action in our problem is over here. But actually, the action within the cylinder of an internal combustion engine starts on this side of the piston. This is a spark plug, and these are valves. And one of these valves opens, and incidentally, they move this way. You see, up and down like this, and this up and down like this, to allow gases to either move into or out of the chamber. Well, one of the valves opens, and a mixture of gas and air move into the chamber. The spark plug creates a spark, an explosion occurs, and the explosion causes the piston to move this way in the cylinder. So the piston moves this way in the cylinder, and the crank then is caused to move around like this. And here's the crankshaft. So here's the connecting rod, the crankshaft. And in this process of many, many times going through that explosion idea and the piston moving this way, the crank is moving around the crankshaft. The crankshaft is powered in that way. There are several cylinders involved in this process. An 8-cylinder engine would have the 8 of them. So that's what gives the power to the automobile. Anyway, in this problem, we have a situation where we have a 7-inch connecting rod, a 3-inch crank, and it is this distance x that's changing as the piston moves this way in the inside the cylinder. All right, and this is the angle theta that's being referred to. So theta is changing, x is changing. Now the 3 and the 7 are constant in this situation, but it's a very dynamic situation with theta and x. Now, so we have a diagram, we understand the nature of the problem, that this theta is changing and this crank is moving around and around, the crankshaft is moving around and around, and actually this theta is changing at, or the rotation is occurring at 200 RPM. Okay, that much we know. We want to know the speed of the piston, how fast the piston is moving through the cylinder at some particular point in time when theta is pi over 3. Now that corresponds with this velocity of the piston corresponds with the change in the distance x. How fast is x changing at that moment in time, and that's what gives us our velocity for the piston. Okay, here's the triangle just in a diagram taken from the previous figure. Now we'd like to have a relationship that in a triangle that involves all 3 sides of the triangle with one of the angles. And from trigonometry, we know all about right triangles, but with triangles that are not right triangles, there were 2 fundamental relationships. One was called the law of sines, the other the law of cosines. And it's the law of cosines that involves all 3 of the sides and one of the angles. The law of cosines is this: a squared is b squared plus c squared minus 2bc cosine a. The important thing in this relationship, or in this formula, is that a and this capital A, this angle A, side A and angle A are opposite one another. So we're talking about a side of length 7 and the angle of theta as being opposite one another. So the angle A is really theta, and the side A is 7. And the other 2 sides are just filled in for the B and C. So a squared means 7 squared, the B and C, now these are interchangeable parts. I'm letting B be the 3 and the C the x, and then filling in for the B and the C here, and cosine theta we can clean up a little bit and it becomes this. Now this relationship is going to be used in 2 ways. We have this notion of implicit differentiation that will give us, that would get us to the velocity point. We also have the notion that at a moment in time that theta is exactly pi over 3. The opening of theta is exactly pi over 3. It's important for us to understand the difference between theta and the velocity of theta at a point, the difference between x and the change in x at a point in time. So, I mean, let's talk about that a little bit. We know that that derivative is instantaneous rate of change. That's a good way to think about it in a problem like this. So for the variables x and theta, x being this distance, theta being the angle opening, what about that instantaneous rate of change? The derivative, the dx dt, means the instantaneous rate of change of x. And that instantaneous rate of change of x is the velocity of that piston. So that's what we're looking for in this problem. The d theta dt, which is going to occur, it's going to crop up in our differentiation process in a minute. But this is also an instantaneous rate of change. And it's the instantaneous rate of change of the angle theta. Now we know something about that from the problem. We know that the we have a situation where we're going around and around 200 RPMs, 200 revolutions per minute. So that instantaneous rate of change is at 200 RPMs, but every revolution, you see, is 2 pi. You see, in terms of radians, and we want to express this in terms of radians. So this is 200 times 2 pi, or 400 pi radians per minute. That is the rate of that angle opening. Okay, now let's go through, and for a specific theta of pi over 3, when theta is pi over 3, how long is that distance x? We're going to need that when we take this implicit differentiation. We're going to need that information. So let's go out to the side and figure it out. All we have to do is use this relationship here and plug in a pi over 3 for theta, and then we'll be left with only the variable x, and we'll solve for x. So here we go. We have, let's see, cosine pi over 3 is 1/2. And then 1/2 of the 6 is 3, so we have minus 3x here. And manipulating a bit, throwing the 49 to that side, we get negative 40 when collected with the 9 that's already over there. And I'm bringing down the x first, and this becomes the minus 3x, and these two give us the negative 40. Factoring, we get x minus 8 times x plus 5, the values of x that cause each factor to become 0 or 8 and 5. Now, since x is a distance, the only one that makes sense is the positive value, so x is 8. Well, now we're ready, with x being 8, we're ready to go into the implicit differentiation and get at these instantaneous rates of change ideas that will provide an answer to the problem. All right, I've repeated the equation up here, and by implicit differentiation, the 49 becomes 0, this becomes 0. Now here we would have 2x dx dt. And then for this part, we're using the product rule, and we'll have minus 6x times the derivative of cosine theta, that's minus sine theta, and this is d theta dt. And then we have cosine theta times the derivative of this, which is negative 6, and all of that part is a dx dt. Okay, now look at the three, we have 3 terms in the problem. We have a term here, a term here, a term here. A couple of them are dx dt's. Okay, now it's dx dt that we're trying to solve for here. That's what we're trying to find. So we're going to put the terms involving dx dt on one side of the equation. I've taken this term and I've thrown it over here, and I've taken this term and thrown it to the left side as well. This is minus 6 cosine theta dx dt, and since dx dt appears in both of these, it's easily factorable. So we have minus 2x plus 6 cosine theta dx dt. And on the right, we have this, and cleaned up, let's see, minus times minus plus, this is 6x sine theta d theta dt. Now, I'm going to go ahead and solve it. At almost any point in time, we can plug in information that we know from what we just previously calculated. For example, we know that d theta dt is, I think it was 400 pi. So we could plop that in here, right here, if we want to. A lot of times it's kind of handy, though, to manipulate into a solution point. That is, solve this for what we're looking for. We're looking for dx dt. Solve it for dx dt, and then do your plug-in. So that's what I've done here. And dividing on both sides by the binomial, I get this fraction, and now I just pop information into the fraction. And we found x to be 8. We know that theta is pi over 3. d theta dt is 400 pi. This x is also an 8, and the theta is pi over 3. And punching a calculator or manipulating this just a bit, we find that dx over dt, the instantaneous rate of change of x, is negative 4018. Now, and it's inches per minute, incidentally. The lengths or the distances that we were talking about, the connecting rod and the crank, were in terms of inches, and the time was in terms of minutes that we saw earlier. But the negative 4018 idea is this. Come back over here, and let's make sure we understand why this is negative. We're talking about the speed of this piston, and it's like x is declining, decreasing, you see, and this distance is decreasing, and that's why it's a negative amount. And if it were an increasing, it would be a positive amount. But anyway, it's negative 4,018 inches per minute. And if you change this into miles per hour, you'll find out that it's not very fast in terms of miles per hour. And I'm suggesting miles per hour because it's what we have a reference to, sort of. We kind of get a pretty good feeling for how fast it is if it's in miles per hour. But it isn't very fast. But keep in mind that 200 RPMs is not a very high number of RPMs for an internal combustion engine. A television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation S equals 50t squared, where S is measured in feet and T is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change in the elevation of the camera at 10 seconds after liftoff. So here we're freezing time at 10 seconds after liftoff. We start with the space shuttle, and we have a liftoff in a situation where a camera is 2,000 feet from the liftoff position. And then the shuttle lifts off, and at some particular moment in time, we have the angle of the eye of that camera, and we'll call that camera angle theta. Now we know that the position of the shuttle is defined by an S, and we have an equation for making the calculation of S. Okay, well, with this in mind, since we know something about we're in a right triangle configuration, we have an angle involved, we know something, have information about the opposite side and the adjacent side, so we're talking about tangent. Tangent theta then is S over 2,000. Now we want to differentiate implicitly here, and for tangent theta we know that the derivative of tangent is secant squared, so we have secant squared theta, and this is a d theta dt. And on the right side we're thinking of this as 1 over 2,000 times S, and the derivative of S is simply 1. So it's 1 over 2,000 ds dt. Now, what are we looking for here? Well, we're looking for the d theta dt, and to solve for d theta dt, we'll multiply on both sides by 1 over secant squared theta, and then we get this. Now let's go through and work with each part of this. The 1 over secant squared theta is probably a little easier to think about this as cosine squared theta. So now, but dealing with cosine squared theta from the perspective of theta, we need some information about the hypotenuse. Well, that's no big problem because we have some additional information about our problem. S is 50t squared, and we're freezing time when t is 10. So when t is 10, S is 5,000. You see the t would be squared to give 100, and then 50 times 100 is 5,000. So S is 5,000. Now, calculating the hypotenuse is no big problem. Hypotenuse squared is 5,000 squared plus 2,000 squared, so the hypotenuse squared turns out to be 29 million. And the hypotenuse itself then is the square root of 29 million. Well, now we can talk about the cosine of theta, and of course cosine squared theta. Cosine theta is 2,000 over the square root of 29 million, and since we were talking in the previous step about cosine squared theta, all of this is to be squared. Then the 1 over 2,000 just comes down. The ds dt, though, is rather interesting. Now, this is the derivative of S with respect to time. We can just go to our basic position equation and find that. The derivative here, or the S prime here, which is ds dt, is 100t. So the ds dt then is replaced with 100t, but we know that t is exactly 10. And then we punch our calculator to find the approximate value of all of this expression. It turns out to be 7/100ths radian per second. Now the degree equivalent to that is approximately 4 degrees per second.